In many multi-antenna test applications, it's often critical to have simultaneous phase-coherent data acquisition across multiple channels, whether for demodulation, antenna calibration, channel sounding, or beam steering and beam forming. In this presentation, you'll see the Agilent M9703A 8-channel 12-bit digitizer perform phase-coherent multi-channel signal measurements using real-time digital down conversion capabilities to optimize the bandwidth and sensitivity for each signal being analyzed. Using multi-channel digitizers to make measurements on multi-antenna systems, including calibration using a single tone, provides many benefits. When testing the antenna array under dynamic conditions, it is important to simultaneously perform phase-coherent data acquisition from all of the channels. The Agilent M9703A's digitizer clock distribution has been designed with low channel-to-channel skew to optimize simultaneous acquisition. In this example, the same CW signal is sent to two of the digitizer's channels. The Agilent M9703A allows us to measure the phase and amplitude differences between two channels from a common input signal. After a few seconds, we can see that the standard deviation of the channel-to-channel phase difference remains a fraction of 1 degree, with the amplitude differences between channels remaining very stable over time. Increasing demand for greater precision and data capacity has driven up the number and density of antenna elements. Modular multi-channel digitizers have the advantage of easily scaling up to provide a larger number of channels without the use of switches. As radar and antenna test signals evolve from traditional sinusoids to broader band signals such as multitone, chirps, or live signals, a digitizer's wide acquisition bandwidth provides the necessary frequency span to sample these wideband signals. When using a wideband digitizer to capture narrowband signals, the embedded digital down conversion capabilities help achieve greater sensitivity and better measurement resolution, and help you tune and zoom on your narrow spectrum content of analysis. The digital down converter's implementation allows phase-coherent post-processing across multiple channels. Agilent's digital down conversion, or DDC, provides three key functions. It sets the analysis bandwidth around the signal of interest by shifting the center frequency in the DC to 2 GHz frequency range. It reduces the bandwidth and sample rate to the appropriate values for the signal being analyzed, and triggers on the signal of interest at a specified frequency and bandwidth thanks to the magnitude trigger. In this first example, the DDC is tuning a 300 MHz CW tone, and the decimation and filtering stage reduces the span to 800 MHz. Note that the noise floor is about -80 dB. In this next example, the DDC will use a higher decimation ratio of 8 to reduce the span to 100 MHz. Note that the noise floor has been reduced after decimation to -90 dB. These results are measured with an input signal at -40 dB of full scale to challenge the sensitivity of the digitizer at full bandwidth. This last example will use a decimation ratio of 128 to reduce the span to 13 MHz. Note that the noise floor has been pushed down to -110 dB from full scale. These functions deliver the key advantages for your application by isolating the signal of interest from other signals reaching the ADC, improving the analog performance by reducing the amount of noise, and extending the amount of capture memory. Put Agilent's M9703A real-time digital down conversion capability to work on your most challenging multi-antenna test applications.